and this video is going to be about the first problem, number of connected components. So let me explain you the problem. So what does the problem state? The problem states you'll be given a grid of size n cross m, where n is the number of rows and m is the number of columns in the grid, and zeros are meaning water and 1 is meaning the land. Okay, so your task is to find the number of islands, and an island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically or diagonally in all 8 directions. So basically what they are stating is they'll be giving you a grid of size n cross m. Okay, over here 0 means water, 1 means land. Now you have to find the islands. So this is a land, this is a land, this is a land, this is a land, this is a land. So I can say these all lands are connected. These all lands are connected because this can be connected like this, like this guy is connected to 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 this. Or you can take the other way. These guys are connected, these guys are connected, these guys are connected, these guys are connected. They are connected in somehow because all the 8 direction connectivities are allowed. All the 8 direction connectivities are allowed. So I can say these piece of lands are connected. And then there is water. And then this piece of land is connected. And this piece of land is connected. So apparently I find 3 pieces of land or 3 pieces of island. First island, second island, third island. So there are 3 islands. So the question states, tell me the number of islands. Tell me the number of islands if I give you a grid. Now you might be thinking, but Shriver, this is a 2D matrix. How can this be a graph problem? This is a graph problem. So try to think it as a node. Try to think this as a node, 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 a node. So all these guys as a node. Okay. So if you think that all of these guys as a node or a vertex, carefully observe. This guy is connected to this guy. This guy is connected to this. This guy is connected to this. This guy is connected to this. So can I see? If I start the traversal, it can be any traversal, BFS, DFS, doesn't matter. If I start a traversal from 1, this will make sure it traverses the nearest one. This will make sure it traverses the nearest one. This will make sure it traverses the nearest one. This will make sure it traverses the nearest one. So if I start from a particular one and I do a certain level of traversal, assuming that the connections are in all the 8 directions, then this one will go and traverse this. This one might go and traverse this. This one might go and traverse this. This one might go and traverse this. They cannot go beyond this because there is 0, 0, 0, 0, 0, 0, 0, 0, 0 all over. They cannot go beyond this. So if you do a traversal starting from this one, this will go and touch all of these guys. And that can be called as one entire BFS or DFS, whatever you do. So I can do one traversal and that will touch this, right? And then can I see? From here, if I start the next traversal, this will touch these 2 things. And the third traversal, if I do from here, it will touch. So can I say, in short, if I do 3 traversals, 3 starting nodes, one can, like, out of these, I can pick up anyone as the starting node, and it will make sure it visits everyone. Again, among these 2, I can pick up anyone as the starting node, and it will make sure it will touch these 2. And from here, I can pick up anyone, and this will make sure it only touches it. So can I say, if I take 3 starting nodes, yes, if I take 3 starting nodes, I will be able to touch all the pieces of land. Thereby, can I say there are 3 islands? Because one starting node will make sure it touches all the connected lands. So one starting node will represent 1 island. So this is the intuition. So we have understood kind of the intuition. But how do we apply a traversal technique that we have learned in the previous videos? So we know a couple of traversal techniques. One is the BFS, while the other one is the DFS. So probably we can just try the BFS traversal technique, and then we can think of something. Okay, so what does BFS state? BFS states, give me a starting point. So I'll say, okay, this is the initial starting point. And you can just refer this by, instead of node numbers, you can refer this by this row 0 and column 1. So it can be the starting node can be represented as row 0, column 1. So instead of a vertex number, we can represent it by a row and a column number now, a pair of row and column. So I can say this is the starting node. Now, what did we do initially in the BFS, if you remember? Initially what we did was, we took a queue, right? We took a queue and we inserted the vertex. And what is the other thing that we did? We always went ahead and marked them as visited in the visited array. But over here, the vertex numbers are in pairs. So we need something as a 2D array to mark visited. So what we will do is, we will create a replica 2D array, yes, a same size 2D array can be easily created. Yes, a same size 2D array can be easily created. So please go ahead and create the same size 2D array. Once you have done this, this is 0 and 1 pushed into the queue. Initial config, 0 and 1 will be marked as visited or 1. So this is the visited array. Please mark them as visited. Done. What is the next thing that you will do? We will like fine. What does BFS set be? BFS set be while traversal, pick up the element from the queue. I'll pick up the element from the queue. Perfect. And then it said travel to all its neighbors. And in the graph, we stored all the neighbors in something which was known as adjacency list. Remember? But over here, what we will do is, we don't have an adjacency list, but we know who are the neighbors. If I'm standing at a node, the neighbors can be someone at the top, someone on this diagonal, someone on this diagonal, someone in this one, someone here, someone here, someone here, someone here. There are 8 directions who can be neighbors. We know the 8 directions. We know that there can be 8 directions. So what we will do is, we will go to all directions. So does it have a neighbor on the up? So that does not exist. Does it have it here? No. Does it have it here? Yes, we have someone, and that's on the row 0 and column 2. Row 0 and column 2. So go and mark it. Perfect. Next, does it have it here? Yes, that's on row 1 and column 2. Row 1 and column 2. Mark it. Next, does it have it here? Yes, that's on row 1, column 1. Mark it. Next, does it have it here? No, it's a water. Does it have it here? No, it's a water. Does it have it here? Invalid. Over. So I decided all the 8 boundaries and I got 3 guys who were lands. Take it, and we are done for the first traversal. For the first traversal, we are done. Let's pick up the next guy, which is 02. Now who is 02? This guy is 02. Checks for all its neighbors in the same way. This guy is already visited, does not take. Already visited, does not take. Already visited, does not take. Does not gets anyone. Perfect. 1, 2. So we get 1, 2 now, which is this guy. So we have 1, 2. So for 1, 2. This is visited, water, water, water. We get a new guy who is at 2, 2. So 2, 2 is marked as visited. Perfect. Then water, marked as visited, marked as visited, marked as visited. So this guy only got this neighbor in all 8 directions, which we have taken. Perfect. Next we get 1, 1. And 1, 1 is this guy. Again, visited, 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 water, 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 water. Done. 1, 1 is also done. Next we get 2, 2. At 2, 2 what happens? Which is 2, 2. This is this. Visited, water, 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 visited, visited, visited. So we get no more neighbors. Thereby, 2, 2 is also done. Apparently, the queue becomes empty. Apparently, the queue becomes empty. So this is how, if you do a traversal, you will touch this, 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 this. So you saw how in one traversal, you could have done DFS as well. How in one traversal, we were able to touch everyone, the lands that were connected to it. Done. Next, we have to start from this guy, which is the starting point will change. And this time the starting point will become 4, 0. And again we'll follow the same process. And if we follow the same process, again it will be marked, right? So the next time the starting point will be this, which is 4, 3. Again the same process, and this guy will be marked. So apparently there were 3 starting points that we used. So how will you decide the starting points? Very simple. What we will do is, we know it's a matrix. So we start from this guy, which is 0, 0. And we say it's a water. No need to do. Next we go to here, we find it's a land. We start the BFS traversal from a land. And this is my first starting point. And this will make sure it visits everyone. Next, we got this is done. Next we go to this. And this says, I'm already visited, man. Someone visited me. No need to do a BFS. I cannot be a starting point because I was already. Next we go here, water, water. He says, hey, I'm already visited. Next we go here, already visited. Water, water, water. Again, this guy says, I've already been touched. Water, 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 water. Next you come over here and you say, I have not been touched, I've not been visited. You need to consider me as a starting point, and this will touch both these guys. Next you go here, he says I'm touched. Water. Next you go here, I'm not touched, I'm not visited. You have to do a starting point as me. Okay, so you got 3 times as the starting point. You got 3 times as the starting point. So if I kind of tell you the pseudocode, now you know the BFS traversal is kind of simple. So if I tell you the pseudocode, it's going to be somewhere like for the row number. Like if I say row is going to be from 0 to n, and then there will be column number, which will be from 0 to m. And what you say is, if not visited, row and column, what you do is you call the BFS with those row and column, and at the same time you say these are the number of starting points that I called for. So apparently this portion will count every time you call a row column to be the starting point, you count it, and BFS will stay kind of similar, only you just make sure how to traverse in the adjacency list. So we kind of wrote the pseudocode. So I'll now get back to the editor and I will tell you how to write the code like step by step. Again, the Java code is on the left and we're writing the C++ code on the right. So just in case you have an issue, you are following Java, you can definitely check out the left part. Okay, so what are we given? We're given the character grid 0 or 1, it will recommend water. So what's the first thing I told you? We need to create, we need to get the n. So n will be very simple. You can just say grid.size, that will give you the n. And we need to get the m as well. So you can say grid of 0.size, right? That's something which you can say. What is the next thing that you will do? You need to create a visited array. So since we need to pass everything by reference, it's better we create something like this, okay? And we need to create visited. So vector of int and m comma 0. So everything is marked as 0. Now what is the next thing that you will do? You will be like, okay, the rows will be from 0 and rows will go till n, and there will be row plus plus. And then there will be columns. So columns will be from 0, columns will go till n, and column plus plus. Perfect. And now what you'll say is, if not visited, row column, right? Then you can just keep a counter plus plus, and you can call the BFS for this row column with this visited and with this grid. And at the end of the day, you can just go ahead and return the number of components, which is the number of islands. And over here, you can just initialize count equal to 0. Now your time now to write the BFS code. So let's quickly try out the BFS. So what I'll do is, you can write the BFS as well. That is completely your choice. I'll leave it to you. So writing the BFS, you can write DFS as well. I'll show that to you as well. So INT row, okay, INT column, that's the starting point. Now the next thing that you'll do, you'll take the visited guy. So visited guy will be taken. Always make sure you pass with reference, and then you can definitely take the grid as well, which is this. And once you've done this, you come back to here. Now the first thing that you do always, you say visited of yes, that's the initialization, equal to 1. What's the next thing that you do? You took a queue, but this time since you're carrying a couple of guys, please make sure you carry something like this. And you say queue.push of row, comma, column. Done. What's the next thing that you do? You iterate on the queue. Simple BFS guys. Iterate on the queue, right? And you get the row as queue.front.first, and you get the column as queue.front.second. Once you have got the row and column, you just pop in queue. Simple. And this was a part of your BFS. If you remember, in the BFS algorithm, you stored that into the BFS, but now we are more concerned about just going and marking it, right? Now we need to traverse in the neighbors. Traverse in the neighbors and mark them if it's a line. This is what we need to do. Now the question comes up, you need to traverse in its neighbors. So which are its neighbors? So I'm going to teach you a shortcut for this. So apparently, if you are standing at a row column, let's come back to the iPad. If you're standing at a row column, which is kind of a portion, now it will have a neighbor as the upper guy. It will have a neighbor as this 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 guy. This, and this. So either you can write 8 neighbors separately by writing 8 different lines, or there's a shortcut. So this is row and this is column. What will be the index above row? That's going to be row minus 1 column, right? What will be this? This will be row minus 1 column plus 1. Perfect. This will be row, comma, column plus 1. Perfect. What will be this? This will be row plus 1 column plus 1. Perfect. This will be row plus 1 comma column. Perfect. This will be row plus 1 column minus 1. Perfect. This will be row, comma, column minus 1. Perfect. This will be row minus 1 column minus 1. Perfect. So if you carefully see, everything is like minus 1 row. How is row varying? Minus 1, or it's like the row, or it's like row plus 1. This portion is row plus 1, this is row, and this is row minus 1. How is column varying? This is column minus 1 and column plus 1. So everything is varying from minus 1 to plus 1 in both row and columns, right? So what you'll do is, you'll run a couple of loops, and you can call it as delta I or something like this. Delta I or delta row goes from minus 1 to plus 1. And similarly, you can call delta column from minus 1 to plus 1. And this will, for the neighbors, you can say the neighbor row is row plus delta row. And you can say the neighbor column is column plus delta column. This will give you the neighbor row and the neighbor column very, very easily. Why? Because first time it will be minus 1, this will be minus 1. So first time it will be like minus 1, which does have. Next time it will be minus 1 and this will go to 0. So minus 1 plus 0. Next time it will be minus 1 and plus 1. So minus 1 plus 0. So you will actually come across every neighbor. If you just follow this technique, you don't have to write them individually. You will automatically come across all of these neighbors, right? So let's go back to the code and now try to get all these neighbors. So here like delta row equal to minus 1, delta row greater than equal to this, right? And then you say delta row plus plus. Perfect. And then what you do is delta column will be what? There might nothing be on the top, or they might be crossing boundaries. So make sure the neighbor row is valid, which is this again, which is you need to make sure you need n and m, so you can again just recompute them, or you can carry them from them. So grid.size, and you can say grid 0.size will be your column size. Perfect. So you can say this has to be valid, thereby this has to be this, and obviously n column has to be greater than 0 and an n column has to be less than m. This is for valid. Once they are valid, they have to be very, very important. Once they are valid, they have to be a land, which is something like this. They have to be a land, and what's the next thing? They have to be non-visited as well. So the new row and the new column have to be non-visited as well. So you need to make sure you write all these conditions. Yes, you need to make sure you write all these conditions together. Like first you check for validity, then you check for land, and then you check for visited. And if all of these are satisfied, you can just go and do n row, n column equal to 1, that's visited, and you can say the queue to please go and store the new row and the new column. Once this is done, in this way you can traverse all the neighbors, and you can just keep on doing the same BFS traversal. And once, by the way, just make sure this is land as well. Grid of the row column has to be land as well in order to do a BFS traversal. Perfect. So now what you can do is you can just go across and run the code, and if you see the output is correct, it does run fine, and your task will be to probably try DFS, and the DFS traversal, just make sure these are the neighbors and everything else will stay the same. So this is how you can easily use the BFS algorithm in something like a matrix in order to solve a particular problem. So let's discuss the space complexity at first. So what are we using? We're using a visited matrix which is taking n squared. Now a lot of you might argue that we can use the given matrix only to mark visited. Yes, you can use that, but generally even if you're using that, in order to solve the problem, you're using space. So you're using big of n square space in order to have your visited stuff. Whether you do it on a grid or whether you create a separate array, that doesn't matter, but you're using big of n square space. You can explain that to the interviewer. And there is there any other space? There is a queue space at max n square queue space. If all of these guys are connected, the queue might end up like given matrix only to mark visited. Yes, you can use that, but generally even if you're using that, in order to solve the problem, you're using space. So you're using big of n square space in order to have your visited stuff. Whether you do it on a grid or whether you create a separate array, that doesn't matter, but you're using big of n square space. You can explain that to the interviewer. And there is there any other space? There is a queue space at max n square queue space. If all of these guys are connected, the queue might end up taking n square space, but that will not happen. That is a very, very rare case. That's not going to happen. So yeah, we can say the space complexity is near about big of n square. What about the time complexity? We're running multiple loops. Like if you look at the code, like it's n squared over here, and then you're calling BFS. But if you won't be calling for every guy. Like it is not possible that everyone is 1 and you call BFS for everyone. That's not going to happen, right? So in total, you over here call BFS for once, twice, thrice. That will not happen. You create a separate array, that doesn't matter, but you're using big of n squared matrix only to mark visited. Yes, you can use that, but generally even if you're using that, in order to solve the problem, you're using space. So you're using big of n square space in order to have your visited stuff. Whether you do it on a grid or whether you create a separate array, that doesn't matter, but you're using big of n square space. You can explain that to the interviewer. And there is there any other space? There is a queue space at max n square queue space. If all of these guys are connected, the queue might end up taking n square space, but that will not happen. That is a very, very rare case. That's not going to happen. So yeah, we can say the space complexity is near about big of n square. What about the time complexity? We're running multiple loops. Like if you look at the code, like it's n squared over here, and then you're calling BFS. But if you won't be calling for every guy. Like it is not possible that everyone is 1 and you call BFS for everyone. That's not going to happen, right? So in total, you over here call BFS for once, twice, thrice, like 4 times, 5 times, 6 times, 7 times, 8 times. So it is kind of 8 plus you traversed for n square plus n square is what you traversed, like you to find out this first one. So it'll be like not happen. That is a very, very rare case. That's not going to happen. So yeah, we can say the space complexity is near about big of n square. What about the time complexity? We're running multiple loops. Like if you look at the code, like it's n squared over here, and then you're calling BFS. But if you won't be calling for every guy. Like it is not possible that everyone is 1 and you call BFS for everyone. That's not going to happen, right? So in total, you over here call BFS for once, twice, thrice, like 4 times, 5 times, 6 times, 7 times, 8 times. So it is kind of 8 plus you traversed for n square plus n square is what you traversed, like you to find out this first one. So it'll be like if everyone is marked as 1, so the BFS will travel like n square nodes. If everyone is marked as 1, the BFS will traverse n square nodes, right? And then there are neighbors, that is like 8 neighbors for everyone. So you're going to check 8 neighbors for everyone. So n square nodes into 8 neighbors is what you're checking. So you're checking 8 neighbors. But you might argue, but Trevor, this will be running for like 3 into 3, 9 times. But out of that, 1 time will be ignored. Why? Because when del row will be 0 and del column will be 0, it means the current row and column, which is like, it will be like row plus 0 and column plus 0, but you'll find that as visited, so it will not go there. So apparently you're going for n square nodes, and for every time you're finding 9 neighbors or 8 neighbors. So it's like n square into 9, and then you're traveling the matrix. So it's something like n square for the matrix in order to check for ones, and then you're doing a BFS like n square into 9. So roughly n square you can call the complexity as. So the time complexity will roughly boil down to n square. If you want to go into deep, you can just analyze it again and again. You will be more confident about this. So guys, I hope I was able to make you understand this particular question, because it has a lot of concepts. So just in case you understood, please make sure you like this video. And if you're new to our channel, what are you waiting for? Hit that subscribe button right away. And yeah, with this, I will be wrapping up this video. Let's meet in some other video. Till then, bye bye, take care. By the way, SD sheet and the DP series, the link are in the description. Please make sure you check them out. Bye bye, take care.